It is the nature of mankind to explore. We are by definition curious creatures. And ever since we peered out of the cave, we've been asking questions. We look up and see stars and wonder what they are and why they're there. We look down and see the earth we stand on. 1,000 more questions come to mind. Where did this come from? What is this made of? And then we ask, how do we fit in? This exploring and questioning has shaped the modern world. It has taken us from the rifts and valleys of Africa to the world of today with all its comforts and benefits. But at the core is still the big question. How do we fit into all we can see and know? We look as far as we can to the outer reaches of the universe, using all that we have learned to find the answers. We peer into the tiniest particles of matter, atoms and parts of atoms, and everything in between, all to answer this question. We still are asking many of the same questions that early man asked. What are we made from? Where did the elements come from? But today, we're asking them with a wealth of knowledge accumulated over the centuries. The studies of nuclear science, particle physics, and astrophysics, and the questions they raise about fundamental building blocks of nature and their interactions, all provide clues to the answers. Making sense of all the information coming from these wellsprings is what concerns scientists today, as we struggle to learn how the complex evolved from the simple beginnings we now partially understand. Our quest began with a very simple thought, all the way back in ancient Greece.
What's absolutely amazing to me is 2,000 years ago, probably even longer ago than that, the Greeks were wondering, what are we made out of? What are the fundamental building blocks? And Democritus said, well, maybe, I'm paraphrasing here, I'm paraphrasing the original Greek, maybe there are fundamental building blocks called atoms, just maybe. And so asking this simple little question, what's stuff made out of, has led us to this amazing story about how we got here from the beginning.
The concept of the atom dates back to about 450 BC, when Democritus hypothesized that a substance can only be divided so many times before it can be divided no more. That smallest, indivisible particle would be an atom, the most basic structure of that substance. Unfortunately, 900 years later, in 450 AD, the philosopher Aristotle didn't agree, concluding the world was made up of only 4 elements: earth, water, air, and fire. It wasn't until the 17th century that scientists began using the applied theory of Francis Bacon's methods of observation and inductive reason to explain the intricacies of nature, and not until the latter part of the 18th century when John Dalton created the atomic theory, based on the assumption that atoms do exist. This theory underlies all of chemistry today. There are 4 major parts. 1. Everything is made of atoms. 2. Atoms of a given element are unique and only look like that element. 3. Atoms are neither created nor destroyed in a normal chemical reaction. They are combined and rearranged, but never destroyed or created. 4. A given compound always has the same ratio of elements by mass. For instance, water will always have 2 atoms of hydrogen and 1 of oxygen. Now, Dalton didn't actually discover anything. The tools of his day didn't let him see an atom, but he used his theory to explain the observations of the time in terms of natural laws. But he still didn't have it quite right. The atom was not the most basic particle.
So J.J. Thomson, like many of his contemporaries at the time, was playing around with what happens with basic electricity. Well, we're calling it electricity now. It wasn't known as electricity then. So he has this electrode in a vacuum glass tube, and he's trying to understand the properties of this ray that he has produced. So he puts a negatively charged pole close to the ray and sees it repelling, puts a positively charged side and sees it attracting. So from that, he surmises that this, whatever it is, has to have a charge, and it has to be a negative charge. They didn't know if it was a particle or a wave, so he had to work with collaborators and say, well, is it seems to travel in a straight line, so it must be a wave. Other scientists at the time were saying, no, it's focused, so it must be a particle. So by the time he actually discovered it was a charged particle beam, that was the discovery of the electron. And actually, the biggest impact of J.J. Thomson, besides his discovery of the electron, was really leading a way of thinking with his students. It really transferred to Rutherford, Chadwick, and Oppenheimer eventually. So it was really this new way of thinking. The world was all new, whether we are doing particulate matter or wave matter. So this dual nature of matter was very much at the heart and soul of many scientists and all kinds of scientific work at the time.
Thomson later measured the charge-to-mass ratio of an electron, and another researcher, Robert Millikan, was able to determine the charge of an electron. But there were still questions about mass. Where did it come from? What makes things have weight? It was another tabletop experiment that provided the answer.
Rutherford was actually just coming off winning the Nobel Prize in Chemistry the previous year for his work on transmutation of elements in 1908. And at that time, they'd discovered the alpha and beta and gamma radiations. And in fact, Rutherford discovered gamma radiation. And he decided that one could use the alpha particles coming from radioactive decay to probe the atom, to try and learn something about the inner structure of the atom. So I think the commonly held assumption was that the atom was some kind of plum pudding, what do you want to call it, in which you could embed these electrons in, and then the whole thing would be charge neutral. So what they did was they made a thin foil and fired alpha particles through it, and most of the time they just went straight on through, but very occasionally they would be scattered through very large angles. And this is really very much like a meteor or something like that coming through the solar system. The solar system is very big. If the meteor goes through the outer reaches of the solar system, not much happens, but if it comes in anywhere near the sun, it has a huge deflection. And so he realized, after they'd thought about this for a while, that what was happening was that the mass, rather than being distributed over the size of the atom, was concentrated in this nucleus, a very small amount. So 99.9% of the mass of the atom is actually concentrated in the nucleus at the center of the atom. And that's also where the positive charge is. And at that point, he called the nucleus of the hydrogen atom the proton, the first nucleus. And so that was, if you like, the first building block of the nucleus that had been identified.
Using observation and inductive reasoning, scientists had been working to make sense of the merging information. But it was a curious man named Mendeleev who provided the insight that led to the periodic table we use today.
Mendeleev was a very interesting character, and among his many attributes is he was a fantastic teacher. And wanting to teach chemistry better to his students, he tried to conceive of a way to organize the known elements so he could explain their chemical properties. And so what he did was he wrote the name of the element and some of the chemical properties on a card. And then he started playing a kind of card game to organize them to see if there are any patterns. One version, the version that we use today, is the vertical columns are arranged by the chemical properties of the elements, and the horizontal rows are arranged by atomic number. Now Mendeleev arranged things by the only thing that he knew, which was atomic weight. That is how much these things weighed relative to other things. The real contribution that Mendeleev did, which no one else had done up to that time in searching for these patterns, was that when he got to a missing point, he said, well, maybe there's an element there that just isn't known yet. And so he skipped them over and put the next known one in its proper place in his table. Mendeleev predicted these elements that would be found, and it was less than 10 years after his prediction where the elements were discovered, and not only were found to have the appropriate atomic weights they were supposed to have, but also to have the chemical properties that Mendeleev predicted. So to have someone finally predict the properties of one of these elements that would be discovered caught people's attention. And they recognized that there must be something fundamental. There must be something underlying this sort of vast array of now elements that we're finding in nature. And of course, nowadays we understand that fundamental nature is the number of protons in the nucleus, and then therefore the number of electrons that are associated with that, and then the chemical properties that arise from that.
As we reach the beginning of the 20th century, the sciences are exploding in every field by leaps and bounds. Man has taken to the air. Technological engineering wonders abound. The Panama Canal is underway. Mighty ocean liners are built. In Bern, Switzerland, a patent clerk named Albert Einstein unites space and time in one mathematical description called the theory of special relativity. When war breaks out in 1914, science changes the battlefield forever, and governments take notice, and the race to fully understand the secrets of the atom is on.
They know that the atomic number is the number of protons in the nucleus. So they go to measure the atomic weight, and it's very different. There's a lot missing. In some factors and in the earlier nuclei they're studying, it's almost a factor of 2. Rutherford had a gut feeling for how things worked from his studies of discovering the proton. But at the same time, there were German physicists who were playing around with the same beams. So here you use an alpha beam, put it on a material, and they had used beryllium as a available and plentiful material. And off come some very energetic particles that they think might be gamma rays. So the French are very interested in this too. They've picked up the experiment and they think, well, if it's gamma rays, let's measure the energies. And that's where Chadwick comes in, because he's been paying attention, and Chadwick and Rutherford are both very skeptical about the discovery that that both the French and the Germans claim might be emitting gamma rays. They don't believe it's gamma rays. And they do a series of more experiments.
Using a cloud chamber filled with nitrogen, Chadwick noted atomic collisions happening away from the source of radiation without any proton trails leading to the collisions. From this, he deducted that particles approximately the same size and mass as protons were causing the recoil in the nitrogen atoms, but that they must be uncharged, otherwise their paths would be revealed in the chamber.
So here Rutherford and Chadwick finally identify a neutral particle which is approximately the same mass as a proton, but slightly larger, very slightly larger. So now you could look at the atomic number and say that's the number of protons, and look at the atomic weight and say that's the number of neutrons plus the number of protons. So it all made sense.
With the nature of atomic weight and atomic number revealed, scientists began to ask more questions, and this requires a closer look.
Probably the best way to find out about what something's made out of is to read the label. It's cheap and easy, but in lieu of not having a label, you have to do something else. Maybe you have to open the can yourself and peek around inside, or maybe in frustration you could just break the can open and discover what's inside. Physicists have found that unfortunately it's the last thing that usually you have to do, and there's a whole industry of scientific research that involves smashing things apart to find out what they're made out of. And that's really the beginning of what's led to our fascination with large accelerators. Those are the tools you use for looking inside. Nuclei are positively charged, and the particles that you collide with are also positively charged. Alpha particles, protons, have positive charge. Consequently, there's a Coulomb barrier that repels these particles, and that barrier is very strong. In order to get over that barrier and to cause nuclear reactions, you need to make the incident particles more energetic or make them move faster. You're limited with alpha particles from nuclei to about 5 million electron volts. That's the unit you use for measuring the energy of the alpha particles. And you really need much higher energies. And also you need energetic protons and other particles for making collisions to sensibly understand what's inside nuclei. So only a few reactions were accessible to the early pioneers in this field, using alpha particles for the reactions, and they missed most of the interesting nuclear physics, and that only came when accelerators were invented, which had the capacity of making much more energetic beams of charged particles to shatter nuclei with.
The first particle accelerator capable of breaking apart an atom was devised in 1929 by J.D. Cockcroft and E.T.S. Walton in the Cavendish Labs in England. This early device used alternating current and a chain of capacitors and rectifying circuits to produce strong electric fields. Protons injected into the space between the fields were accelerated into targets. The bombardment of the atom had begun. Cockcroft and Walton first disintegrated lithium by firing a proton into the nucleus to produce 2 alpha particles. In 1934 in Paris, Irene Curie, the daughter of scientist Pierre and Marie Curie, bombarded aluminum with alpha particles to make a new, unstable isotope of phosphorus, which then decayed radioactively to a stable isotope of silicon. They had artificially produced, for the first time, a radioactive substance, which until then, scientists had found only in nature.
Nuclear systems and atoms are mostly characterized by the number of protons in the nucleus. That's responsible for the number of electrons, and it makes the chemical properties of the atoms that are made up of these particles. But it's also possible, because nuclei are made out of protons and neutrons, to have a given number of protons and a different number of neutrons. These isotopes were a major discovery of nuclear physics. They came in a time where it wasn't well understood that neutrons and protons made up nuclei. The original model was that protons and electrons were the substance that made out of nuclei. With the revolution that came after the discovery of the neutron, the realization that there were isotopes was a major change in thinking. And what was realized at the time is that there were many isotopes that could exist that didn't necessarily exist in nature, and that with nuclear reactions you could create these isotopes, isotopes that may have been briefly formed during cataclysmic supernova explosions or major cosmic events, but no longer exist because they're too short-lived. But with particle accelerators and with nuclear reaction, you could make new isotopes. And many of these new isotopes are of fundamental importance in understanding the overall structure of nuclei and the overriding theory that describes how the nuclei are formed and how they live their lives.
For the first time, scientists are creating new forms of elements in the lab and realizing that there can be more than one variation of one type of element. These new versions are both stable and unstable and are named isotopes. A well-known naturally occurring unstable isotope is found in carbon. 98.9% of carbon on Earth is called carbon-12. It contains 6 protons and 6 neutrons, adding up to 12, hence the name. But there are 2 other forms of carbon found in nature, one known as carbon-14. Carbon-14 contains 6 protons and 8 neutrons, or it has 2 extra neutrons. It is an unstable isotope, or radioactive, because one of these extra neutrons eventually transforms into a proton, making the atom a 14 nitrogen nucleus, with 7 protons and 7 neutrons. Since all elements sharing the property of 6 protons are carbon, carbon-14 with its 2 extra neutrons is an isotope. Archaeologists today measure the amount of carbon-14 in a sample to accurately date objects through a process known as carbon dating. While there are relatively few naturally occurring isotopes on Earth, many more exist in the cosmos.
In Mendeleev's table, it's organized by atomic number. But there's another kind of chart called the chart of the nuclides, which is organized according to number of protons going up in the chart and number of neutrons in the nucleus going to the right or left. The number of neutrons in a nucleus determines what its atomic mass is, and that determines the physical properties. So the protons determine the chemical properties, and then how many neutrons and protons there are determine its physical properties. It determines how much it weighs, it determines what it does if it's in the center of a star reacting with other nuclei, and other properties like that. So for us studying isotopes, that's the chart that lets us map out or lets us see the relationship between the various kinds of atoms. One of the questions that we're trying to answer is how many different kinds of atoms could exist? And by different kinds of atoms, I mean, well, how many different numbers of protons, how many different atomic numbers, how many elements, and then for each element, how many different numbers of neutrons can we put in the nucleus and still make an atom? If we have too few neutrons in the nucleus, then the electric repulsion of all the protons there just pushes it apart and it doesn't make an atom anymore. And that limit is called the proton drip line. There's an equivalent neutron drip line where at some point they just don't stick anymore. And so if we put one more in, it, say, drips off. You can think of it like a cup and putting drops of water in a cup. At some point you just fill the cup up and you put the last drop in and it won't stay, it just drips off the side. And that we call the neutron drip line. Now, remarkably, we don't know where those limits are. And it's one of those fundamental pieces of knowledge that tell us about the nuclear force, the strong force that binds atoms together, that we want to know, and that will give us greater insight into the nature of nuclei and atoms.
There are relatively few naturally occurring isotopes on Earth, but in the lab, many isotopes can be created through collisions and recombination. Again, some of them are stable. Many more of them are unstable or radioactive. It is the study of these isotopes that drives nuclear science, or the study of the nucleus. In order to create enough collisions to study these isotopes, new and better accelerators began to develop.
The early accelerators, the first ones that were developed, were basically big batteries. They made big electric fields, not with a battery, but with a power supply. And then they used these electric fields to accelerate charged particles. Another mode of accelerating particles is the ideas that came with the circular machines, the cyclotron and so forth. And those machines used an idea of, well, it's similar to the way you get a swing to start swinging. A swing is a pendulum, and the way you make your kid swing a great distance is not to hold them out to a large distance and let the swing go. That's possible, but it's hard to do that. What you do is you push on the swing, and you push on the swing in rhythm to its oscillation. Each time it oscillates, you give it a little more energy, and eventually you build up a large amplitude of oscillation. And you do this by synchronizing your pushes to the swing of to the frequency of the swing. Now it's a pendulum, and it turns out a pendulum has a nice feature. The frequency of the pendulum is independent of the amplitude. So you can push with the same rhythm continuously as the amplitude builds up. And this really is the idea that led to the cyclotron.
If you put a charged particle into a magnetic field, comes in, you know, here's the field, here's the particle. The particle is bent in a circle inside the field, so it goes around in a circle. But interestingly, for a given magnetic field and a given particle, given charge to mass ratio of that particle, the frequency that it goes around the circle is independent of the speed of the particle. As it goes faster, the circle gets larger, but it's moving more quickly, and those two effects exactly balance. So the particle, the frequency with which it rotates in the field, which is called the cyclotron frequency, is a constant. So that means if you have apply an oscillating voltage and apply it at the right moment and the right frequency, and you tune it with a tuning fork or whatever it is, you can repeatedly accelerate a particle as it goes around. And that was the principle of the cyclotron. And Lorentz had that idea, and his first one was very small, but he made it work out of glass and sealing wax and brass and so on. And after that, spent the rest of his life scaling it up to larger and larger such accelerators. So the first cyclotron, I said, was quite small, but pretty soon he wanted to go to an 11-inch cyclotron, and then a 37-inch cyclotron, and a 60-inch cyclotron, and each one needed a larger magnet and more space and more power. And so he was facing, and there was at that time no National Science Foundation to go to get funding, and no Department of Energy. So he did what he had to do. He went to the university, he went to private donors, he went to the local power company, telegraph company, who had magnets they'd used in World War I. One of his machines was funded by a University of California regent, who was a wealthy man who gave him money for that. And then finally, just at the outbreak of war, the biggest machine, which involved moving up here on the hill from campus, was funded by the Rockefeller Foundation. So he worked very hard to get private donations and private foundations to fund his research long before he received funding from the government. But that did change when war broke out, because then there was a particular need for cyclotrons and so on, and separating isotopes, and that brought the government into the equation. But he'd been working hard to fund his research for many years before that happened.
Lorentz was not only a great scientist, he was a miraculous entrepreneur. He was one of the first scientists who learned to organize large teams. These teams didn't just include physicists. They included engineers and technicians and people devoted to a project. And that was the scale of things that were necessary to build these big machines that he was contemplating. They required all kinds of talents, and he would assemble these talents, but it was really beginning to be too much for what could be supported by an ordinary academic institution, and particularly in the physics department. So he moved out of physics and formed what was then called the radiation laboratory. The radiation laboratory would be devoted to these large team efforts. That was really the beginning of what has become today big science. It was really Lorentz's innovation, and it brought a level of organization to science that really hadn't been seen before. The previous mode was one professor working with some assistants in a small laboratory. This was more of the industrial side for science, and maintaining that through that period was one of Lorentz's other great contributions, in addition to his technical innovations and his vision of accelerator physics and how that would have implications for high energy physics and nuclear physics. That became the model for the Manhattan Project, and this big science became too big for the private benefactors that had previously contributed to scientific research. And the federal government at that time, generally following the war in the later part of the 40s, started investing in big science. You could make the argument that there would be great innovations, great discoveries, and these discoveries would be important for the benefit of society.
For many centuries, science, frontier science, could be conducted basically in your lab, often just by a lone researcher or maybe 2 or 3 collaborators. And that's because when you make discoveries, typically, especially in the physical sciences, you are creating an apparatus that is testing the behavior of nature at the limits. And for the longest while, those limits had not yet left the laboratory. Latter 19th century, beginning with the 20th century, we were done in the lab. We reached a period where, to test the limits of nature, we needed machines that could sample the energies of the universe at much greater levels than could be contained within a lab. We needed telescopes that were no longer pieces of optics that you would just simply cart to your backyard. Even Edwin Hubble, Hubble the man, after whom the telescope was named, he's responsible for discovering the expanding universe. He did that, yes, he did it alone, with some other people's research supporting it, but he did it with the largest telescope in the world. A telescope that he did not build, somebody else built. A whole other contingent of people got together to make that telescope a reality. And so this this consistent ascent of size and scale continues to this day.
In 1946, the first of many national laboratories is created, and along with the universities, they will carry forward big science in the United States. The government continues to invest in a variety of research and science venues, and by the 70s, new Earth and space-based observatories are collecting a wealth of knowledge about the universe, which help answer the questions of how elements are created. But a more in-depth understanding of astrophysical processes is required. The challenge becomes how to bring a little bit of the stars down to Earth and simulate the reactions that take place inside them in accelerator facilities. It evolves that the overarching goal of nuclear physics is not reductionism, but how to explain the emergence of complex structures from more fundamental components.
There is a lot of overlap between particle and nuclear physics still today. There are fields where they are actually common terminologies, but there is one significant difference. Particle physics in its essence is reductionist. It always tries to bring things down to the simplest particles, the elementary particles, which are governing nature. Nuclear physics does not try to discover the most fundamental particles. Nuclear physics takes a number of particles which you know their properties about and then address the question, how do we compose other nuclei? In other words, most of the matter which we are seeing in the universe is made of atomic nuclei, and we are asking ourselves the question, how do we put the individual building blocks, protons and neutrons and electrons together to build the visible world?
If we look at the various kinds of atoms we find in nature, all the elements, the things that have higher atomic weights than iron, they must have been produced in some sort of a process by which neutrons were captured into the nucleus, or which neutrons hit the nucleus and stuck in some very energetic environment. And early on, people recognized that there must be 2 pieces to this. There must be kind of a slow process where over time neutrons are captured, and that's called the slow neutron capture process, or the S process. It happens over hundreds of thousands of years. But that can't explain all of the heavier elements, the higher atomic weight elements. It can only explain about half of them. The other half, the only way that we can understand that they must have been created was by some very rapid capture of neutrons. So our process is this very rapid neutron capture process that has to exist somewhere. Based on what we know about atomic nuclei, we can say what the conditions must be like. We can say that there must be phenomenally large numbers of neutrons present, and this process must happen at very high temperature, and it must happen very quickly. By high temperature, I mean it has to happen at a few billion degrees Celsius, and it has to happen only in a few seconds. And so that makes you think, well, okay, it sounds like maybe a star exploding.
A supernova is the explosive death of a star, and like all true deaths, it only happens one time. And for the star, it's a transition to a new state in its middle. The middle of the star collapses to a neutron star or a black hole. It's so bright you can see it halfway across the universe. It puts out as much energy in a few seconds as the sun will put out in 10 billion years in its whole life. A star is it's a big phrase, a gravitationally confined thermonuclear reactor, by which I mean gravity is always pulling it down, trying to force it to go to a point, and it's making it hot. Because it's hot, it radiates, and so it has to get its energy from somewhere. It gets its energy by fusing lighter elements into heavier elements. And this is its whole life. It makes hydrogen into helium, and helium into carbon and oxygen, into heavier elements. In a massive star, that process goes on all the way to the most tightly bound element that there is, iron. But once you've made a core of iron, about 1.5 times the mass of the sun, there's no more energy to be obtained from nuclear reactions, and yet it's still being pulled down by a fierce gravity. It's radiating neutrinos and light. And so it collapses under its own weight to a neutron star or a black hole. And that collapse liberates a huge amount of energy. So while the middle of the star falls down, some of the energy released in the collapse gets transferred out and blows the rest of the star off, and that's what makes the supernova. Now, when it blows up, the supernova launches the explosion out as this blast called a shock wave, because it's running out much faster than the speed of sound. And as that runs into the matter, it does two things. It pushes it off the star, but it also makes it very hot. And in that high temperature, a brief frenzy of nuclear reactions happen called explosive nucleosynthesis. And we think the way that works is that in its collapse, the binding energy of the neutron star is released as neutrinos. Particles that have almost no mass and travel close to the speed of light. They're electrically neutral. They can go through a light year of lead. But there's so many of them that just a few of them interact with the material falling down on the baby neutron star and begin to inflate a bubble full of radiation and electron-positron pairs, and the pressure of that radiation causes an expansion whose boundary is a shock that pushes out the rest of the star and blows it off. So most of the elements made in the supernova were actually made before it ever died. The layers of hydrogen and helium and carbon fusion that were going on get shoved off. It's all neutrons and protons. And it's mostly neutrons, in fact. So the neutrons and the protons join together, and all the protons go with neutrons to make helium, and then helium to carbon, and so on. And there's a lot of nuclear reactions that we really need to study. But eventually, it ends up making things in the iron group with a lot of neutrons left over. And those neutrons add on, tang, 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 one by one, very fast, going all the way up, making elements as heavy as uranium. And that rapid process of neutron addition is what we call the R process.
Now, we know that during those stellar explosions, the nucleosynthesis, the synthesis of new elements, is going through isotopes which don't exist, which are very short-lived. These are the rare isotopes we want to study. So if we ever want to understand how the material which makes up our Earth was created in the universe, we have to understand what was happening in those stellar explosions, and in order to understand that, we need to study these rare isotopes.
In the United States, isotope research is conducted at several facilities, including many of our federally funded national labs. In 1978, on the campus of Michigan State University, the National Superconducting Cyclotron Laboratory was commissioned as a user facility and began providing research facilities and support for scientists from around the world. The facility operates today under federal grants from the National Science Foundation to serve the broad international community of nuclear scientists.
It's big, and it looks and sounds complicated. And it is, but it's still easy to understand. You just have to know where you're going and follow the path from start to finish. The path is the beamline, and on that path are the nuclei. All the equipment here in the laboratory at NSCL is designed to simply accelerate those nuclei to half the speed of light, smash them into a target, and study what's left over. The journey starts here with the chart of the nuclides, which is a lot like the periodic table, except that it's more complete. We'd like it to be even more complete. We start with a larger element than the isotope we're looking for, so when we smash it, maybe one of the pieces left over will be the isotope we're after. The first step in creating our beam is here at the ion source, where we will insert our selected element, heat it up into a gas, and then bombard it with free electrons. This knocks some of the electrons off of the element, which is now a charged ion because it's missing some of its negatively charged electrons. Now we can move those ions with electromagnetic forces, steering them down the beam line to the next step, which is the accelerators. Here at NSCL, we use two powerful cyclotrons in succession to accelerate nuclei up to half the speed of light. As our beam of speeding nuclei pass through the target, some break into pieces. The parts coming out of this collision are what we want to study, or at least some of them are. We need to sort out the pieces we're not interested in, and that happens at the next stage of the beam line, the A1900 fragment separator. This equipment uses specific tuned magnetic fields to steer the isotopes we are looking for along a designated path. Other isotopes don't make the turns because they have a different charge or mass, and therefore their path doesn't bend the right amount through the magnets. These isotopes fall harmlessly by the wayside, while the rest pass through other separators along to become a pure beam of the destination isotope we want. This beam is then directed to a vault where it is analyzed. There are several vaults where we can send the beam, and each is home to a different experimental detector, such as the S800 spectrograph, MONA, the modular neutron array, LEBET, which stands for Low Energy Beam Ion Trap, and SEGA, which is the segmented germanium array. Each detector has a specific purpose, allowing the researcher to study some particular aspect of the isotope of interest. This helps us run our laboratory more efficiently for the users who come from all over the world. Everything's monitored here in the control room, where operators tune the equipment to produce the isotopes and diagnose the beam. The data is all stored on computers for analysis by our researchers who come to use the laboratory. The result is we run 24 hours a day with different teams coming and going and sharing equipment and ideas. There's a tremendous sense of professionalism and cooperation and excitement as experiments reach critical points along the way. We're bringing researchers together from all over the world, helping them share knowledge and methods and driving them in entirely new directions. This is truly a dynamic and fun place to be.
Today's researchers and scientists continue to explore on the outer edges of what we can observe and measure. What are the limits of atoms? How many different elements are possible? What is the nature of the force that holds nuclei together? These are the modern versions of the questions we have asked since the beginning of mankind. And just as one set of answers reveals itself, new questions arise in the continuing cycle. The journey of discovery to this point has been eventful, but it is far from over. In the small matter of big science, there is much more to come. In the future, new technologies and advancements in understanding will require further investments in resources, and as we continue the search for origins, exciting applications of cutting-edge science will continue to shape the world in which we live. Understanding and managing these investments will be a key to prosperity as we face the challenges of the years ahead. For although no one can say for sure what the next big thing may be, we can say with certainty where it will come from. The frontiers of science.